In this lesson, we're going to talk about electric charges and how electric charges interact with each other and how they can be transferred from one object to another. Let's imagine that Francine is walking across the rug wearing leather-soled shoes. When she gets to the other side, what happens? Her hair stands up. She thinks that the carpet is charged electrically, and her hair is being pushed away from the charge on the carpet. Is she right? To understand the answer to this, we're going to look at electric charges, and to get a deeper understanding, let's look at charges at the level of the atom, at the atomic level. So an atom is made up of three main pieces. The proton is a positively charged part of the atom. That's in the nucleus, in the center. We also have the electron, which is a negatively charged particle that is on the outside of the nucleus. And in the center also we have the neutron, which has no charge. We're not going to consider neutrons for electrostatics because they don't have a charge, so they won't affect any calculations we need. When we measure charge in an atom, we use the unit of a coulomb. In the next lesson, we'll talk about Coulomb's law, so you'll see that Coulomb was the person who really researched electrostatics. We abbreviate coulombs with a capital C. The fundamental charge is called E. It's a lowercase e. It is the charge of the proton and the electron, the difference being the proton is positive and the electron is negative. But in terms of charges, the smallest possible charge we can get is the fundamental charge, the E. You can't take an electron and cut it in half, or a proton and cut it in half. So our fundamental charge is always going to be E. That's our base for charges. So the charge of a proton is going to be positive E, and E is measured in coulombs as 1.6 times 10 to the negative 19th coulombs. This is on your AP equation sheet, so you don't need to learn it. We abbreviate charge with the lowercase q. So the charge of a proton is a positive E, which is this. An electron is going to be a negative E, so it's the same value but with a negative sign in front of it. And a neutron is a charge of 0 coulombs. The other thing we should note is that there is a difference between the mass of a proton and the mass of an electron, and this is important when we get into looking at momentum and other things, or also for forces. So the mass of a proton is much larger than the mass of an electron. You can see that proton is 10 to the negative 27 kilograms, and an electron is 10 to the negative 31 kilograms. And a neutron has the same mass as a proton. All right, so now we've talked about the basics of charge in an atom. Another big idea that we use in electrostatics is that charge is conserved. Charges can't be created or destroyed, so when we create a charged object, we haven't created charge. All we've done is moved charge from one object to another. So let's suppose we have two atoms that are neutral. They both have an overall net charge of 0. They have 5 positive charges and 5 negative charges, so that the sum of charges is going to be 0 for each. Now the protons are going to stay inside the atom. They're tightly bound. They're not likely to leave the atom unless there's some deeper nuclear reaction. We're not going to be talking about that in electrostatics. But the electrons are more loosely bound. It's easy to remove an electron from an atom, especially in certain types of elements. When you rub objects together, for example, for friction. So if you were going down a slide and this child rubs against the slide, some of that friction will cause electrons to transfer between the child and the slide. And so what it looks like on the atomic level is an electron moves from one atom to another. The result is the first atom now has lost a negative charge. It now has a positive 1 charge. And the second atom has gained a negative charge, so it now has a charge of negative 1. Note that the total charge for both atoms is still 0. Charge has been conserved. It's just moved from one object to another. So let's look at this specifically one type of transfer of charge called friction. So let's say we have a piece of wool and a plastic rod. They start with a charge of 0. Overall, there's no charge, but there are charges. It's just that they're exactly balanced in both objects. Now we're going to rub the rod with the wool, and the friction will cause the negative charges to move from the wool to the rod. And it will look like this. We now have more negative charges on the rod, and they were lost from the wool, so now it's positive. So note that the total charge isn't changed, but some of the electrons have moved from one object to the other. Charge is conserved. So this is called transfer of charge. It's by friction. Friction is when charge is transferred from one object to another by rubbing the two objects together. This is what is going on when Francine is walking across the rug. She's having friction between her shoes and the rug. Now, you don't need to memorize this, but leather-soled shoes generally lose electrons. If she were wearing rubber-soled shoes, she would be gaining electrons. So as she's walking across the rug, she's going to lose electrons. Those electrons go into the rug and leaves her with a net positive charge. So she thinks the carpet is charged and her hair is being pushed away from the charge in the carpet. Is she right? Well, she's partly right. Yes, the carpet is charged. But her hair is being pushed away from itself because the positive charges, these like charges, repel each other. So her hair is pushing away from the charges in the hair, not from the charges in the carpet. So the general rule for two charges is if we have two charges that are like, that means they're the same, like a positive and a positive charge, or a negative and a negative charge, they push away from each other. Like charges repel each other. And you can see here two positive charges have forces pushing them away from each other. If we have two objects with opposite charges, a positive and a negative charge, they have an attractive force. So opposites attract. Opposite charges, positive and negative, have forces pulling towards each other. We'll talk more about forces when we talk about Coulomb's law. But notice that these charges are equal and opposite forces on each other. The magnitude of this force is exactly equal to the magnitude of this force. The magnitude of this force is exactly equal to the magnitude of this force. Equal and opposite forces should sound familiar from AP Physics 1. What do you think? Well, Newton's third law says forces come in equal and opposite pairs, and that's what's going on with the charges. There's another way that we can create a charge in an object, and it's by induction. So we have a rule that a neutrally charged object, that's an object with no charge, is attracted to a charged object. So let's say you charged up this pen with a wool scarf, and you held it near just pieces of paper. They are attracted to it. What? How does it make sense that an object with no charge in it has an attraction towards something that's charged? Well, here's the explanation. Let's say we have a neutral sphere. This is like the pieces of paper with equal charges. There's no net charge on it. We bring a positively charged rod towards it. What's going to happen when we have positive charges pulled close to this sphere? Well, the negative charges in the sphere are attracted to the rod, and the positive charges are repelled. So as a result, we have negative lines up on one side of the sphere and positive lines up on the other side. The result is we have an overall net force towards the object, and that's because the pushing away force is further away. Since it's further away, it doesn't have as large of a force. We're going to talk about that more later, but overall, we end up with a net force pulling it towards the positively charged rod. This is when we can do this with a neutral object and make it have a negative charge on one side and a positive charge on the other, this is called polarization. So the uncharged object is polarized. The positive and negative charges are separated when a charged object is brought nearby. This is called charging by induction. We're not actually touching the object. Charging an object without actually touching it is called charging by induction. So this is now a polarized or charged object in terms of this side has a negative charge and this side has a positive charge. Finally, the last way we can charge objects is by conduction. This is the most obvious way of charging objects. We just take a charged object, we touch another object, and we pass the charge on. So for example, the first way we could do it is we could have a negatively charged rod, we could touch a neutral object. These negative charges repel each other, so they try to spread out. So they're going to move onto the ball. So now we still have an overall negative charge. It's smaller on the rod, and now we have a negative charge on the object. So both of them end up with a negative charge. We could also have a positive charged object that we touch a neutral object with. And in this case, the negative charges from here are going to move over here, leaving a positive charge on here and a smaller positive charge on here. So in the end, we end up with two net positively charged objects. Those are charged by conduction. The last thing we're going to talk about is the types of objects we can use. When we are going to charge things, sometimes we want to insulate things so that the charge doesn't leave. An insulator is an object where the materials, it says an object made of a material where the charges don't move. The valence electrons, the electrons on the outer shell, are tightly bound. So an insulator would be something like styrofoam or certain pieces of plastic that don't conduct or don't transfer charge easily. We use those to isolate your Van de Graaff generator or to isolate your any object that you want to build a charge on. We also have conductors. Those are objects that it's easy to transfer charge through them, something like metal. And in those objects, the valence electrons are free to move throughout the metal. It's easy to transfer charge using a conductor.